Hmm. Okay, looks like my Wi-Fi is not very good right now. Let's see. Okay. Can you guys see the screen and hear me all right, or not really? Can you let me know in the chat? Okay. Okay. Yeah, just let me know if it's hard to understand me. Kind of difficult to see. Okay, I'll try moving it a little closer. There we go. Okay, well, it says network bandwidth is a little low. All right, let's see. I guess, I mean, I think we'll just have to keep trying. Okay, so I'll try to write bigger, I guess. All right. So the idea here is going to be, oh yeah, so the first observation we have to make is the top half of the baskets that we don't get to keep, we should fill them up as little as possible, right? It's never going to hurt to fill them up as little as possible, right? So what I mean by that is, let's say, oh man. Okay, let's say you have K baskets. Oof, it's really going to be marked that actually work. Anyways, the first two baskets, the ones that you fill up with the most, you don't really care. You don't really care about them besides filling them up to your minimum, right? As in, if you're going to fill them up with, like, let's say 4 and 5, you might as well have just filled up the first one with 4, right? Because it never benefits you to give, you know, the other cow more more berries, right? You might as well keep it as much as you can to a minimum. So you, like, the lowest amount that you're going to give to the first half of baskets should be the amount that you give to all of them. So this should also be a 4. If, for example, you're giving both of these 4s. Okay. Then we have, and then we can kind of see how to fill out these two, right? And seeing how to fill out these two, it's like, it's kind of, at that point, it's a greedy task. Like, you're just always going to try to fill them up with the tree that has the most number of berries left. And of course, these values cannot exceed these values. Oh boy. All right, let me take a moment to see what's going on with my Wi-Fi. Give me a sec. All right. Can you guys hear me? Yeah. How's the video now? Are you guys able to see the video? Better? Okay, we will go with that then. All right. Okay, cool. So I think I'll just repeat what I was saying earlier because it probably got cut off mostly. Okay, so basically, right, we're filling up these baskets. Half of them we don't get to keep, like the half with the most number of berries we don't get to keep, and the half with the least number of berries we do get to keep. So, you know, for the half where we're not getting the berries, there's no need to give them any more than we have to, right? And so I think the example I was going over was saying, let's pretend we were thinking of giving, like for the half with the most number of berries, you know, we'll give one of them 5 and we'll give the other one 4 berries, right? Well, if we think about it, there is really no point, like there's never going to be any benefit to giving a basket in the half we don't get more than like the minimum, right? Because we might as well just give this guy 4, because I mean, we're not getting these berries anyway, so it's kind of a waste if we give it to him. And like, that is the first observation we have to make. We don't want to give them any more than we have to. Okay. And now comes kind of the problem of the second half of like determining how many berries we get using the baskets like we, you know, that we are actually allowed to keep. And so for these, we can actually, it's a pretty simple idea actually. So let's just pretend, you know, from here, we just subtract 4 from any 2 of these trees. And it doesn't actually matter which ones we do. So let's just say we took 4 from here, so there's 2 left. And we take 4 from here, so there's 4 left. Okay, so now we see that, okay, for these 2 remaining baskets, we want to fill them up with the trees that have the most number of berries left. There isn't also where we cannot take more than any tree has. Sorry, we cannot take more than the minimum basket in the first half has, right? Because if we took 5 berries and put it in here, then this basket actually wouldn't be part of the, you know, the second half, right? Because the second half is supposed to be the least berries. And if you can, that's right, I have a 5 here, because all of these numbers are supposed to be less than or equal to these numbers. So, you know, you have a cap of 4, clearly. And so what you'll do is you'll just look through all the trees and you'll just take as many berries as you can. Like basically you'll take berries from the tree with the most number of berries. And so, okay, this one has 4. So, you know, we definitely want to take it because that's the max out of all these. So we take it, that becomes 0. And then we see, oh, okay, here, that's also a 4. That's the max or the current max. So we take it, it's gone, and we can fill it up here. And then we see, okay, you know, we just add up all these numbers in the second half, and that's our answer. Okay, and so now the way that we're going to do this for the problem is, and also another reason why we are able to do this for this problem and solve it in time is you have to look at the bounds. So the number of berries at any given tree can be in the range of 0 to 1,000. Okay, so at most it can only have 1,000 berries. And so what we'll say is, we'll just consider, okay, what if I assume that the number of berries I'm going to put in the first half of the baskets is like I called it big, I think, when I coded it. So this is like the ones in the bigger half of the baskets. How many are you going to give it? So this can range from 0 to 1,000, and you're going to test all these values. And then for any given value that you're testing, what you'll do is you'll form what's called a frequency, like a frequency graph or list of, frequency table is what the word I was thinking of. Yeah, the frequency table of essentially like the types of baskets you can form, right? So let's just consider right now that big is equal to, I don't know, like 3, okay? And we're gonna consider the sample case again. We have 3, let me see what it was. 3, 6, 8, 4, 2. Right, so and then this is the actual array originally. And then we're gonna have a frequency array, which says where's from a basket of blank berries. So at each of these indexes, this one will represent number of ways you can form a basket with 0 berries. For that, like, this is a special case, we don't really care about it. But then for here, right, and then we're gonna start from the top and go down. And so we're gonna see, okay, how many ways can I form, or how many, like, basically how many baskets of 3 berries can I get, right? And so here I can get 1 basket of 3 from here. I can get 2 baskets of 3 from here, right? Because I take 3 from it, and then I can actually take another 3 from it, right? Okay, so there's 2 here. I can take 2 more from the 8, and I can take 1 more from the 4. Oh wait, can you guys see that? Okay, let me move this down. Okay. Okay. Yeah, you can take 4. You can take 1 basket of 3 from the tree with 4, and you can take 0 from the 2. Okay, and then adding all these up, we get, okay, I can get 6 baskets with 3 berries in them in total. And then you also have to update like your array now, right? Because now when we're calculating, okay, how many baskets of 2 can I form? You're not allowed to, reuse berries from the ones where you already put them into baskets of 3. So this becomes a 0, this is a 0, this is a 2, this is a 1, that's still a 2. Okay, and now you do the same process. You look at, okay, at each tree, how many berries are left and how many baskets of 2 can I form from those berries that are left? And so you see, oh, okay, from this one you can take 2, right? That's 1. And then from this one you can take another 2. And so in total you'll have 2 baskets of 2. And then you do it one more time and you see that, okay, I can get 1 basket of 1, right? That's all that's happening. Okay, and so once we get it into this kind of format, it's very easy to kind of fill up our, baskets, right? Because I'll just say, okay, well, for my first basket, for my first, basically I see, oh, in the first half, can I fill up with, the biggest number, which is currently 3, right? And I can just stick 2 baskets of 3 into there, and then I'll have 4 left. And then I can do the same thing here. I see, okay, of the berries on the right-hand side, the ones that I actually get to keep, how can I fill it up? And the best way, obviously, with these 3s. Yeah, okay. And we can do one more example. So for example, where it might, or just with like a bigger basket size, like maximum basket size. Okay, so we have the same stuff. Okay, and so we see, okay, looking through all of these, how many baskets of 5 can I form? And I'll say that, okay, I can get a basket of 5 from here. I can get 1 basket from there. And then from here, I can get 1 more basket. And that'll leave me with 3 more berries. So in total, I can get 2 baskets of 5. Then you look through the whole thing again, you see, okay, how many baskets of 4 can I get? I can get 1 of them from that tree, which will leave me with 0 more berries at this tree. Then I do the same thing for 3s. I see, okay, there's 2 3s. Okay, I find 1 2. And I find 1 1. Oops. Okay. And now when I'm filling up my baskets, right? For the first half, I have to fill them up with 5s, right? And so I say, okay, these are my 5s. Then for the second half, I fill it up with the biggest remaining ones, right? And so at this point, my biggest remaining ones, 4s. I have 1 that I can, and then that will be my filled, my filled baskets. And so this is the whole idea. And so if we look at the efficiency of this, well, first of all, we see that we're going to be repeating this process, like, because we're doing a for loop on this big variable. We're going to be repeating this process 1,000 times. And then you have to think about, okay, how long does it take to process this? Like putting them into the baskets. And so, well, we see that, okay, we have K baskets, right? Or, okay, I guess before I go there, first, within each loop, we have to create this frequency table, and that takes O of K time. Actually, hold on. O of, is it K time? Because you loop through this a big number of times, like, whatever this value is. And then you modulus each of these. Yeah. It takes, yeah, because for any one of these index, your times can fit into the biggest basket, and then whatever's left always just becomes like a 1 in here, right? So at most that'll be 2 times. So yeah, it's, I guess I should write this out more formally. O of B times, this takes B time to fulfill, and then to put it into the like the baskets, that takes K time to fill, and then that's it. So O of B times B plus K. Well, if we look at the bounds, the maximum values for both B and K are 1,000. So this is around the order of this is around the order of like 10 to the 6th, which is far less than our limit of 10 to the 8th. And so that's why it works. Alrighty, so I think we can just get into the coding part of this now. So I'll share my screen. Okay, so let's take a look at this problem. All right, so we're gonna have a couple variables that we want to make or read in. So you have N and you have K. Read them in. Hey guys, I think I got disconnected there. Can you guys hear me? Let me know in the chat if you can. Okay, okay. Here, I'll just go back to just talking about, I'll just go over everything again. So this part is where we read in the input, and then we are iterating through all of the values of big, where big represents the number of berries we're putting into, like, the bigger baskets, the bigger half. Okay, and so for each time we do that, we have to calculate the frequency array or table. So and we're going to do memset. So memset, just a quick reminder, is all it does is it just sets the entire array to zeros. Okay. And we're going to loop over each of the values. Or we're going to loop through each of the like berry trees, and we're going to essentially put it into the frequency table. So we're going to start off by looking at the number of big, like basically the number of baskets that we can form that are of size big, right? That have big berries in them. And so that's just the tree divided by the number of berries in the tree divided by the size of the basket. And then we have one leftover basket, which is just this, just the remainder, basically the berries that are left over. And then that will calculate our frequency table. And now we can essentially just loop through the frequency array. So we're going to loop through it k over 2 times first, and this will be assigning the big half of the baskets. And then we're going to have a variable called cur size, which this tracks the current size of our basket, right? And so each time we're, quote unquote, assigning a basket, we're just going to first check, do we still have any more baskets that are of cur size? And if so, then we will decrement, we will reduce it by 1, right? That's like uses up a basket pretty much. And then otherwise, oh, I guess I can structure this better. Hold on. Okay, so first I want to make frec of 0 equal, a very arbitrarily large value, because, we can always form baskets with size 0. We have basically an infinite supply of baskets with size 0. Okay, and then here I can change this basically as long as the number of baskets at our current size is 0, we're going to decrease our current size, right? Because basically, let's say, we have a bunch of baskets of size 10, but then we use up all of them. And so once that happens, it'll trigger this loop, and we're just going to keep going down. We're going to say, okay, well, how about baskets of size 9? Can we use those? If not, do we have any baskets of size 8? If we do, great. And then we can continue. Okay. Now we're going to assign, so, the quote unquote small half of the baskets. And we can leave cur size as what it is, right? Because nothing changes about that. we still don't have any bigger baskets, right? We can actually copy this, and we can do current, oh, let me change this to ints. And then while we're assigning our second, smaller half of the baskets, we want to keep track of the number of berries that we get in the second half, right? And so we can just do that like this. And then at the end, and is just equal to max and cur, right? Because this basically helps us take the maximum of all of the curs, when you're through like all of the loops. Okay, so let's see if this works. Also, if you have any questions, feel free to just throw it into the chat and I'll take a look at it. Oh, oops, max B. This can just be 1001. The reason why this can be 1001 is because the maximum size of our basket is 1,000. So yeah. Let's see. Small typos. It's all right. Okay. So we run it and we can look at the out file, and as expected, we got 8. So now if we submit this, we can see what we get. How do I keep it? And look at that, just like that. So I'll just pause for like about a minute, take a moment, just wrap your head around that. If you have any questions, please just send it through the chat and I'll take a look. And yeah. And yeah, as always, I'll send out this code in an email afterwards. But for everyone with no questions, just go ahead to the next problem. I'll send it in the chat. So the next 2 problems are both going to use a concept called binary search, which I think I did briefly cover in the summer. I'll do a quick reminder of the idea behind binary search. Yeah. But yeah, first take a moment, just read through the problem. Yeah. Okay, so yeah, I'll just go ahead, talk about that question now. All right, so Farmer John owes Bessie N gallons of milk, and he has K days to pay Bessie back. And you want to find the largest X such that if you pay Bessie N minus G divided by X rounded down, gallons of milk every day, or M, whichever one's bigger, like that you'll be able to pay it off within K days. You want to find the largest X that'll let you pay it off in K days, assuming you follow that procedure. Okay, so one thing that I guess you can pretty much immediately think of is, okay, what if I just simulate this? I just test. I pick a positive integer X and I test it. You find the biggest one. Well, yes, you could do that. That's a nice solution. It'll take you a lot of time. First of all, to do one simulation, which can be up to 10 to the 12, but also we're going to need to optimize the number of tests you perform, right? Because if you're testing every single possible value of X, well, there's up to about approximately 10 to the 12 possible values there. And so just, no matter what way you look at it, you're going to need to improve that time as well. And so it says my network. Okay. Let's see. Last time, disconnecting and reconnecting. Okay. Give me one. Can you guys hear me? And please let me know in the chat. I do not know. Okay. Okay. Dang. Okay, is this working better? Can you guys hear me? Can you see the board? Yes, awesome. Okay, so yeah, I was just talking about the second problem. So for this problem, yeah, let's first talk about binary search. So let's just assume that we have a test that works. We can basically test any given value of X, and that works fast enough, right? Let's assume we have that already. All right, so given that, how can we find the largest value of X? Well, the idea behind binary search is you're gonna have a left bound and a right bound. And these left and right bounds denote the, it like kind of denotes a range where your final answer could possibly lie within. Okay, and so what you're gonna do is you're gonna look at the middle value, right? We're gonna look at the middle value and we're gonna say, okay, for this middle value, does that value of X work, right? And if it works, then what can we do? Well, if we know that this works, we do not need to consider any of the values below it anymore, right? And the reason for that is, well, this value of M is bigger than all of these values, right? And if we're looking for the largest value of X that works, then we don't have to look at these because we already know that M works, right? M would be the largest one out of all of these. We only need to look in this half, right? To see if there's anything bigger. Okay. And what about if it doesn't work? Well, if M doesn't work, what we know that we don't need to consider anything in the right half, right? Because if M doesn't work, we know that M plus 1 doesn't work, right? Because in the problem statement, that's equivalent to giving Bessie less milk each day. And if you couldn't pay the debt off, giving him this amount of milk, you're not going to be able to pay him off in that amount of time, giving him less milk each day. So we don't need to consider any of these, right? And so that's going to form the general basis behind our binary search. So let's go ahead, write that code right now. All right. So we are here. And I guess, we can read in the input too. That's always pretty simple. All right, let me find it. Okay, so input is just 3 numbers. Very chill. And I'm going to initialize them out here because we're going to be using some, methods that will also want to access these variables. And so now we know that, okay, let's make our left bound. So we're going to use a long. And so, the smallest value of X that we can have is 1, right? Because we're dividing by X. The biggest value of X, this is a little trickier, but we know for sure that it's not going to be more than 10 to the 12th, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We know it's not going to be bigger than this because, at that point, you would probably just be giving him, well, okay, if this was bigger than 10 to the 12th, then n minus g over x would be 0, right? And you can't really pay Bessie off if you're giving him 0 milk a day. I mean, like at that point, you'd just be giving him m milk a day probably. Okay, so we have that. All right, now we're going to be doing our binary search. And so we run this as long as this is true, right? Because as long as our range of possible values is like covers more than one number, we're not done. But if our range goes from 3 to 3, we know that the only possible value our answer can be is 3. So we're going to keep running this as long as L is less than R. Okay, now we'll calculate the mid. So this is how we calculate the mid. You just add them up, you divide it by 2. And in this case, we're actually also adding 1 here. All that means is we're rounding up when we take the average. And I might mention that, the reason for that at the end. Okay, let's assume we have a method called test. Okay, so if test returns true, then we know that this value for x actually works. So like we said on the board, we are going to be changing the left bound, right? We're going to make the left bound equal to mid. Okay, and now in the case that this value does not work, then we're going to make it mid. We're going to make the right bound adjusted, right? Because we can kind of shrink our ranges. Or cut them in half, actually, not just shrink a little. We can cut it in half. And so that is everything in the binary search. Now all that's left to do is code this test. And that part is not easy. Let's make sure this compiles first before we move on. Okay, so this is our binary search. Let me just, this should be a long. And then, yeah. And then at the end, we know that L is our answer because both L and R are the same at this point because of this. And so, yeah. So let's look back to the board and discuss how we can get this test method. Okay. So our original idea, right, is we kind of look through each day one by one, right? We're saying, okay, day 1, we pay, something. Day 2, we pay something. And let's just write out a couple days to see kind of like what we would be paying each day. So I'm going to make up an example. So let's say that N is equal to 100. M is going to be equal to, this is pretty arbitrary, 1, and then X. Yeah, let's say for now, let's cover the case where X is equal to, I don't know, let's just say 10 for now. That's pretty easy. All right, so on day one, how much are we paying? Well, we're paying 10, right? And then, so this is day 1, we're paying 10, and then after day 1, we still owe 90, right? There's 90 left that we owe. All right, and then day 2, it's going to be 90 divided by 10, right? 90 divided by X. And so we're paying 9. Okay. Was this a bad example? Let me see. This is actually an okay example. All right, so we're paying 9. 81. All right, let's look at another case. Third day, we pay 8. And then there's going to be 73 left. Right? Fourth day, we pay 7. Okay, this is not as good an example as I thought, but we'll just stick with it. Okay, on the 5th day, we pay 6. We have 60 left. On the 6th day, we pay 6 again. We have 54 left. Okay, and then let's see. On the 7th, 8th, 9th, 11th, 12th. All right, so on the 7th day, we are going to be paying 5, and we're going to have 49 left. On the 8th day, we're going to be paying 4, and we're going to have 45 left. On the 9th day, we're paying 4, we have 41. On the 10th day, we're paying 4, we have 37. Okay, and then this continues. And so what you see is at the beginning, the amount you're paying each day shrinks pretty quickly, but at a certain point, these values start getting, or like you kind of repeat the amount you're paying. So like you pay 6 2 times this day, you pay 5 1 time, and then you pay 4 3 times. So what we want to do is we want to condense all of the days where you pay the same amount into a single like operation. So we want to be able to compress this into just one iteration of a loop where we just consider, okay, if I'm paying 4, how much do I need to really pay? Let me think if I can, or let me see if I can give you a better example of this. Okay, yeah. Here's a better example. Let's say it was like 29, right? Or let's do 39, okay? If n was 39, on the first day we pay 3, so we have 36. On the second day we pay 3, so we have 33. On the third day we pay 3, so we have 30. On the fourth day we pay 3, so we have 27. On the fifth day we pay 2, so we have 25. On the sixth day, so this is a better example of when you have a lot of these consecutive payments on the same day. So yeah, that's that. Or sorry, a lot of the same amount of payments spread throughout multiple days, right? Okay. And so the way to consider it is, or like to optimize this, is we look at, okay, if my current amount, like on day 1, when I'm thinking about how much I need to pay, okay, well, if I just use the formula, I know that I will have to pay 3 today, right? Regardless. And let's just see how many days, let's try to find a formula for the number of days that I have to pay 3, right? So I know that I have to pay 3 gallons of milk every day that I have at least 3 times X gallons of milk, right? Because as long as I have 3 times X gallons of milk, then I know that if I divide by X and I round down, then the amount of milk I need to pay is 3, right? Okay. So let's get a couple expressions going. So G is going to be equal to the number of gallons already paid, right? And so instead of left, I can actually write N minus G, right? That's the number of gallons left. Okay, so I know that this is how much I currently owe. This is the number of gallons I need to pay today. And we can just let this equal to, current. We can say this is the current payment I need to make today. And then if we think about the minimum number of gallons I need and still pay this much, I know that it's current times X. And continuing with this, all I need to do is I need to take the difference between what I currently have, what I actually owe right now, minus the target amount that I need to reach, right? And then I actually need one less than that. I need to divide by, my target is this. Now I need to divide by the amount that I'm paying each day, which is current, and then I just round up. And this will get me the number of days where I'm paying this current amount. Okay. So this is a lot. Take some time to think about it. Let me know if you have a question about it. Okay. So at this point, right, this is the number of days I need to pay. So it's pretty easy after here. This is like equal to days, right? And then you just subtract the current amount times the number of days you're paying the current amount from this to get your new, you take your current amount times the number of days you have to pay this current amount, and you increase G on this, and you keep repeating until either G is bigger than N or K days have been used up. And then at that point, you can determine whether or not this value actually works. Like this value of X that you're considering actually works or not. All right, so I'm gonna go over to my screen share again. And I'll just talk you guys through this. Okay, so time to implement the test method. So we take a look at this. All right, so this is the current amount already paid, which in the beginning is 0. It's gonna be a long. One important thing to note is you're gonna be using longs for pretty much everything in this problem because the values go up to 10 to the 12, right? Because the maximum value an integer can hold is about 2 times 10 to the 9. But if you're working with numbers that are much bigger than that, it's just obviously not going to work. So that's why we're forced to use longs. And so longs in C++ can store numbers that are up to approximately 10 to the 18th. All right, so this keeps track of the number of, or the amount already paid. We're gonna have another variable called days. This, and I guess we can call this total days. This is the number of days passed in this, like loan repayment period. All right. And so we're gonna just keep doing this as long as this is less than K. If it ever exceeds K, then we know that it doesn't work. Or like if we've used up more days than we have and the amount that we've paid is less than the amount that we owe, which is N, then we know we failed. So G is greater than or equal to N. Okay. So we're going to calculate Y, and we'll just call this, I guess I can just call it cur, right? Cur payment. This is the amount that we're going to pay each day. All right. And then, also we have to now consider M, right? So just in the first case where we assume that the current payment is greater than or equal to, or is greater than M, then we calculate the number of current days, basically days that we have to pay the current payment. And so that's just going to use our formula, N minus G minus X times cur payment minus 1. Put a parentheses in there. Okay, divide by Y. And now one thing you might note is that I don't have the rounding up. And so the way you round up in with like this integer division kind of stuff is you add the denominator minus 1, right? So I just want you guys to convince yourselves of this, that this rounds this number up. If you're dividing by Y, you want to add Y minus 1 to the numerator. So the way to think of this is, right, if your original number is exactly equal to, it's an exact multiple of Y, then it'll divide evenly, right? And you shouldn't be increasing it at all. And if you add, Y minus 1 to that and you divide, all of this will be a remainder that gets truncated. However, if this is at all any like slightly bigger than a multiple of Y, and you add Y minus 1, then that'll be enough to push it to like the next multiple. I hope that makes sense. If not, just try out a few values. Like simulate a few values just, on a piece of paper, and it should be pretty clear why this works. Okay, and now we want to do G plus equal current number of days times current number of payment, right? This is where we're updating amount paid. And then we have days plus equal cur days. Okay, so now one thing to note that I didn't really mention, but is needed, is we don't want the current number of days, or sorry, the total number of days to exceed, we don't want the total number of days to exceed K. So we're going to have just a small thing here where we say that, okay, the current number of days we're gonna be quote unquote doing this payment is just gonna be, it may be the actual current number of days, or it'll be the lesser of these two. Ensures that we don't calculate for extra days. Number of days passed. Okay, so that's all for the case where this current payment is how much we're actually paying. And then now we just need to consider, okay, what about when the current payment is equal to, the amount we're paying is actually M, right? And then at that point, it's just, we know that every single day onwards, we're always going to be paying M, because this is never going to increase as we pay more milk. So it's always going to be M. And so we just say, okay, well, if I'm paying this for all my remaining days, this is how much is going to get paid. Update amount paid for the remaining number of the remaining days, and days is equal to K, right? And that'll break us out of this while loop. And then at the end, we just check, okay, have I paid at least, or have I paid the amount that I owe? And then that's all there is to it. All right. Oops. That's not good. Definitely forgot something. Something here. Oh, my bad. I think I used Y. It's supposed to be cur payment. Mess something else up. No match for operator. Oh, this is supposed to be endl, my bad. Okay, cool. So it compiles. Let's see if it gives us the right answer. And it says 2, and that is right. So it takes 2 days because you give Bessie 5 gallons on the first day and then 3 on the next 2 days, and that'll get you across. Okay, so let's just submit it just to make sure that it works. Oops, looks like I messed something up. Let's see where I messed it up. Okay. Well, I'll first check my binary search, and it looks fine. So I'm going to look at the test method. All right. All right. Okay, I'll spend at most, like 2 more minutes looking through my code. If not, so sorry about this. I do these problems ahead of time, but it seems that I still make some typos. All right, I'm gonna be honest, I don't see it. So I will get back to you guys on this. Once again, really sorry about this, but we have to keep going. We do have one more problem left. All right. So I'll send the link for the last problem. Everyone take a moment to look at it. And then I will cover it in a moment. Okay, so I'm trying to quickly brief you guys on this problem. So essentially, you have n cows that are basically, they're permuted. They're just like arranged in random order, and you want to move these cows through wormholes to get them back to their original locations. And so you have all these wormholes, and each wormhole connects a location A to another location B. You can go either way, so you can go from A to B or B to A. It always works. And you want, and like also each wormhole has a width W. So you want to find the maximum. Basically, you want to find what is the fewest number of wormholes that you can use, such that you can go through the your like fattest cow can go through it. And you're basically asking, what is the fattest like width that my cows can be, such that they can go through all the wormholes with no problem and get to their like correct location. That's essentially what they mean when they say the maximum minimal wormhole width that a cow must switch itself during the sorting process. Okay. And so for this one, we don't have too much time. So I'm just gonna go over the concepts behind it, and I'm not gonna code it. But this is gonna once again use our binary search. Oh, and let me turn on the camera. Okay. And so essentially the thing that we're going to be binary searching on is the width of the cow. So we want to binary search. Oops, that is not the right spelling. Search over the width of the cow. The width of the minimum, sorry, the width of the smallest portal you have to go through. So basically we're going to say, okay, we're going to have a variable called min width be the like for any wormhole, we can go through it if it is at least min width wide. Okay, and now we need to develop our test, right? So our test is going to be, essentially, we are going to use something called connected components. And so I'm going to draw out this first graph. Let's see, so they have something from 1 to 2. And then they have something from 1 to 3. They have something from 2 to 3. And then they have something from 2 to 4. Okay. And so basically what we can say is if we are using wormholes, or like if any two nodes are connected by a wormhole, like a wormhole path, then we can always get from one wormhole to another. So let's say that this wormhole is active, and okay, this is not a very good color because the pen is like nearly dead. Let's say that, oh, I can just do erasing, right? So let's say that, you know, the solid lines are the like the wormholes that, you know, we're saying we are allowed to use, and then the other dotted ones we're not allowed to use. Well, we know that in any basically, like, you know, 1, 2, and 3, these 3 nodes are connected, while the 4th node is just by itself. So we can always get from any of these nodes to each other. So if the cows, you know, 3, 2, and 1 are within this set of nodes, then they can always sort themselves, right? No matter what, because as long as a cow can get to its, like, you know, its target position, basically by traveling through the path, like we know we can sort at least this cow into the right position, right? And so what we want to do is that's going to form the basis of our test, trying to identify these connected components. Okay, and you know, like this 4, maybe it's connected to a 5, which is connected to a 6, right? So, and then these guys can sort themselves accordingly. And so what we need to do is we need to, for any one of our tests, we need to find the connected components. And I think we did a problem similar to this last week with the coloring and the groups. And so you're going to want to refer to that. That's how basically we're using the concept called depth first search, DFS, once again. And we're going to kind of like color these nodes with something. And then we're going to repeat this process for all the nodes. Basically, if every time you find a node that has not been colored, you're going to set its color, and then you're going to kind of look through all of its children and then see if they have a color or not, and then you can set it accordingly. So that's the first step, find the connected components. The next step is we want to essentially check if each cow can get to its original location. Okay, and so the way we can do this is we're going to be using these colors that we set, right? So essentially, we know that we know each cow's current node, so we know the location that each cow is currently in, and we know the destination, right? For example, so the numbers inside these circles are going to be the like name of the node. So these are all of the node numbers. So this is node 1, this is node 2, node 3. And let's say this has a cow, and that's cow 1 in it, right? And then we're going to have another thing called the color. All of these nodes have the color of 1, right? Because they're in the same connected component, we know that they should all have the same color. I guess to make these numbers less confusing, let's say that we're looking at cow 2, which is currently in node 3. So basically, we want to ask, is node 3 connected to node 2, right? Because that's how we want to move. We want to move this cow from its current location, node 3, to its target location, which is the same as the cow itself, right? So if nodes 2 and 3 are connected, then it's all good. And we can see that they're connected because if we check their colors, we see that they're the same, right? So basically, if every single cow can get to its target location, then we know that this test should return true, right? Because we are able to sort it. And if there's even a single cow that cannot get to its target location, then we know that our test fails. And so we should return false. And this is going to be the test that we perform our binary search with. And so, yeah, that's just that's the general idea behind this problem. I know I went over that pretty fast, but I didn't want to hold you guys over too long. All right, do you guys have any questions about that? And, I'll type up some code for this and I'll send it to you guys afterwards, as always. Yeah. Please let me know if you guys have any questions. All right, if not, I think that'll be it for today's class. Thank you guys. Sorry about all the audio problems earlier and the Wi-Fi problems. I'll try to get that fixed next time. We'll see. It's just this location in my house that I'm streaming from. That's pretty poor Wi-Fi. But yeah, all right, thank you guys. See y'all on Sunday, I believe.